So the goal is to find a particular solution, to find a particular solution, to find a particular solution yp of the non-homogeneous equation y double prime plus px y prime plus qxy equal fx. That's the goal. So let's talk about the method 1. So the method 1 is, there are 3 steps. Find two linearly independent solutions, two linearly independent, find two linearly independent solutions of the homogeneous equation y double prime plus px y prime plus qxy equals 0, and we know that this equation can be constant coefficient, so px and qx can be constant. And then it can also be Euler-Cauchy differential equation. Okay, can be a Cauchy-Euler differential equation. So it can be any of them. And then after that, after you find the two solutions, and let's call them y1, y2. So let them be y1 and y2. So the second step, we can assume the solution of the form. So assume yp of the form, we can assume yp of the form yp equal u1 y1 plus u2 y2. So the goal is to find these u1 u2. So where u1 and u2 are unknown functions. Okay, I need to find. Those are two functions that we're going to find. So in the next, what we can do, we're going to solve the two equations. So solve the two equations to find u1 and u2. What are the two equations? One is u1 prime y1 plus u2 prime y2 equals 0. That's the first equation. The other equation is u1 prime y1 prime plus u2 prime y2 prime equal fx. So we're going to solve those two equations to find u1 and u2. And that's the form of the solution. Good. So let's do a problem to see how the method works. So example, find the general solution of find general solution of y double prime plus y equal tan x. So the answer, the characteristic equation of the homogeneous equation y double prime plus y equals 0 is lambda squared plus 1 equals 0. So the solutions are lambda equal plus or minus I. You can write this one as 0 plus or minus I. So that means you're going to get the complex solutions. So thus you can see yc, which is equals to c1 cosine x plus c2 sine x. Now what we're going to do, we're going to pick the two solutions. So this is there's no order here. This is the y1 and y2, the two solutions. So we're going to say let y1 equal cosine x and y2 equal sine x, the two solutions. So now what we can do, we're going to suppose a particular solution. We're going to suppose yp, which is u1 y1 plus u2 y2 form. So in this case it is u1 cosine x plus u2 sine x. Now what we're going to do, we're going to take the derivatives. We're going to substitute this into the two equations. So what are the two equations? So the two equations are u1 prime cosine x plus u2 prime sine x equals, see, that's equation one equation. The other equation is u1 prime, you could take the derivative of this function, plus u2 prime, the derivative, equal fx. Fx in this case is simply tan x. So those two are the two equations that we need to solve. So we want to solve those two. Solve for u1 and u2. So how to do that? Let's simplify this a little bit, because once you take the derivative of cosine, it's become a negative sign. So you might see something little easier. So let's take the derivative. So once you take the derivative, so you're going to get these two equations. So you're going to get u1 prime cosine x plus u2 prime sine x equals 0. I'm going to call this equation number 1. And then also once you take the derivative, this is going to be u1 prime sine x plus u2 prime cosine x equal tan x. This I'm going to call equation number 2. Now what we can do, you can see, you try to create the same coefficient. How to create the same coefficient? Multiply by the missing term. So what we can do, first one you're going to multiply by sine, the second one you're going to multiply by cosine. So we can say by 1 times the sine term, because that's the missing one, plus 2 times the cosine term. So if you do that, you can see the first two terms get cancelled. So first two terms get cancelled, so you're getting u2 prime sine squared x plus u2 prime cosine squared x equal, here you're going to get tan x times, you multiply the second one by cosine, so cosine x. So we need to see how we can simplify this a little bit further. We can notice few things here. If you pull u2 prime out, you simply end up getting sine squared x plus cosine squared x, which is a good sign because we know that this is equal to 1. And what is the tan? So tan means sine over cosine times cosine. So you can see, so this get cancelled, and this is simply equals to 1. So you simply end up getting here sine x. So that means your equation simply becomes u2 prime equals sine x. So this is very easy to solve. So that means u2 equal the integral of u2 prime dx. That means the integral of sine x dx. So integral of sine x is negative cosine x. So we find one function, we find u2. So after you find u2, so the best thing would be, I mean, you can just do the same way, like try to eliminate the other term, but it will be better you can go to equation number 1 and plug in there and solve, because that might be a little bit quicker. So so you can see by equation 1 you can see that u1 prime cosine x plus, we're going to substitute for u2. So what is u2? So you can see that this is u2 prime sine x. So you can simplify this. So if you plug in here, this becomes u1 prime cosine x plus u2 prime. If you take the derivative of this, it's a negative sign. That means it becomes positive sign. So sine and then sine x, which is equal to 0 according to the formula. So now you can just solve for u1 prime. So let's do that. So that means u1 prime is simply negative sine squared x over cosine x. So if you solve for u1 prime, now the question is how to integrate this one. So we're going to think about how we integrate trigonometric integrals in Calc 2. So one way to do that is, you can write the top as sine squared means 1 minus cosine squared x over cosine x. So if you distribute, this simply become cosine squared x minus 1 over cosine x. Now we can divide the terms. If you write this as fractions, you can write this one as cosine x minus 1 over cosine. 1 over cosine means secant x. So you can write it like that. Now what we're going to do, you're going to integrate. So this is a simple integral now. Again using Calc 1 tricks. So u1, which is the integral of u1 prime dx. So that means you're going to integrate one by one. So integrate the first one minus integrate the second one. These are easy. So you're going to see that the first one, this is a cosine, that means it's a sine x. And then integral of secant means the natural log secant tan. So this is natural log secant x plus tan x. So that's a formula that we use. Okay, so we find u1, u2. Now what we're going to do, we're going to plug in. So we have yp, which is u1 y1 plus u2 y2. So let's plug in here. So if you plug in, you're going to get u1 was cosine x, and then y1 was cosine x, and u1 was this big expression, so you're going to put it there. So it is sine x, and then minus natural log secant x plus tan x, and then we have the other one, which is u2 equals sine x, y2 equals sine x, and u2 equals negative cosine x. Okay, so and then you can see that we need to see whether we can cancel. Actually, you can see that the first two terms get cancelled, so those two are going to go away. So that means you simply end up getting negative ln secant x plus tan x. So that means you can have the general solution. So therefore the general solution, which is y equal yc plus yp. So if you plug in, you're going to get c1 cosine x plus c2 sine x minus ln secant x plus tan x. So we don't add any more c's because we only two c's and we only have those two here. So that's the general solution of this differential equation. So this is interesting how it works. And you can see that if you try to use the undetermined coefficient method, it's not going to work for this one, as we discussed before. So let's do another problem, like a different type of problem. How about this one? So we're going to do another example. Let's say find the general solution of x double prime x squared y double prime minus 3x y prime plus 3y equal 4x to the 7. So we're going to follow the steps. The first thing is try to solve the homogeneous equation. So the answer, so consider the homogeneous equation, x squared y double prime minus 3x y prime plus 3y equals 0. And you can see that this is a Cauchy-Euler equation. So this is Cauchy-Euler equation. So if it is Cauchy-Euler, we can use the transform version of that. We have the formula for that. Since we already know about that, we can use the other method for this one, just to learn how it works. So we can assume. So this is how we normally solve the Cauchy-Euler equation. Assume a solution like this, y equal x to the lambda type of solution is a solution. And then what we do, we can take the derivatives. So in this case, then we have, so if we assume a solution like that, then we can see that y prime equal lambda x lambda minus 1 and y double prime equal lambda minus 1 x to the lambda minus 2. Now what we're going to do, we're going to substitute. So if you substitute, you're going to substitute the equation number 1. So we're going to get x squared times lambda minus 1 x to the lambda minus 2 plus, not plus, actually here is minus because that's what we have. So we have negative 3x lambda 1, y prime is lambda x to the lambda minus 1 plus 3, this is x to the lambda equals 0, because we try to solve the homogeneous equation. And you can see this is like, very easy to simplify. So if you simplify, you can see these, when you multiply these two, you get x to the lambda. When you multiply these two, you get x to the lambda. We already have x to the lambda here. So that's the secret part. So once you combine, you're going to get x to the lambda from each term. If you take it out, you're going to get lambda minus 1 minus 3 lambda, and then we have 3, and you can see that you can take x to the lambda out as a fact. But we know that x to the lambda are not equal to 0, because we assume that this assumption, we assume that x not equal to 0, because x equal to 0 is a singular solution. We don't do that. So and then if you simplify what is in the parentheses, you're going to get lambda squared minus 4 lambda plus 3 x to the lambda equals 0. And there are factors. It is lambda minus 3 and lambda minus 1 equals 0. And this can give you lambda equal 1 and 3. So those are the two lambda values. Then we can write the solution. So because we know that x to the lambda is a solution for these lambda values. There are two lambda values, 1 and 2. So therefore we can write the solution. So you can say thus we have yc, which is equal to c1 x to the first value, c2 x to the second value. So if you write, you can write this one as c1x plus c2x cube. Okay. So now what we can do, we can pick these two as the two solutions, two linearly independent solutions, and we know that they are linearly independent. We proved that before. So let y1 equal x and y2 equal x cube. Those two are two solutions. Now what we can do, we're going to go to the original equation. So what's the original equation? It was x squared y double prime minus 3x y prime plus 3y equal 4x to the 7. What we normally do, we're going to bring this to the standard form. So what we do, dividing by x squared. So whatever the term that we have in front, we can divide by that. You're going to get y double prime minus 3 over x y prime plus 3 over x squared y equal, if you divide by x squared, this can be 4x to the 5th power. Good. That's equation number 2. Because we need the standard form, because this is where you're going to get the fx term. So that is the fx term, not 4 to the x7. It has to be in the standard form. Now what we can do, we can assume the solution. So we have assume yp, which is u1, y1 means x plus u2, y2 means x to the cube, is a solution. Is a solution of 2. So thus we have those two equations. What are the two equations? We have u1 prime x plus u2 prime x cube equals 0. That's the first equation. The other one is u1 prime, the derivative of that, plus u2 prime derivative of this equal fx. Fx means 4x to the 5th power. Now what's going to happen? You can take the derivative. So once you take the derivative, you're going to get these two equations again. So I'm going to repeat the pair. So you can see you're going to get u1 prime. Actually, what you can do is you can divide the first equation by x. So if you do that, you're going to get u1 prime u2 prime x squared equals 0. And if you take the derivative of the bottom one, u1 prime plus 3x squared u2 prime equal 4x to the 5th. So those are the two equations that we need to solve. So what we did, we took the derivative of the first one. We divide the first one by x, and we take the derivative of the second one. So those are the two equations that we need to solve. So let's solve them now. So what we can do is we can subtract them. We can subtract the first one from the second one. So by subtracting, we have 2x squared u2 prime equal 4x to the 5th power. And then this you can divide by x squared. You can divide by 2x squared both sides. So then you're going to get u2 prime equal 2 to the x cube. So now we can take this, we can find the other one just by taking the, we can just by integrating. So u2, which is the integral of u2 prime dx. So that means integral of 2x cube dx. So that means 1/2 x to the 4th power. Now what we can do, since we have u2, you can plug into one of those equations, solve for the other one. So we normally use the first one because there are less terms. So we have u1 prime plus u2 prime x squared. This is again u1 prime plus u2 prime. What is u2 prime? So take the derivative of that times x squared, which is equal to 0. It's coming from here. So you can see this simplifies well. So this is going to give you u1 prime. If you take the derivative, you're going to get 2x cubed times x squared equal to 0. So in other words, u1 prime equal negative 2 to the x fifth. That's what you get. Now what we can do, you can integrate this and you can find u1. So let's do that. So this is u1 to the fifth power equal negative 2x to the fifth. So in that case, u1 equal the integral of u1 prime dx. So if you take the integral, you will get negative 2 and x to the fifth dx. So which is negative 2 x to the sixth over sixth. So which is negative 1/3 x to the sixth. So thus we have yp. Yp is u1 y1 plus u2 y2. So let's plug in there. u1 is negative 1/3 x to the sixth. u1 is x plus u2. u2 is 1/2 x to the fourth. y2 is x cubed. And you can see if you simplify this, you're going to get 1/2 minus 1/3 x to the 7th. So this is 1/6 x to the 7th. So therefore y, which is yc plus yp, equals c1 x plus c2 x cubed plus 1/6 x to the 7th power. So that is the general solution of this problem. So this is how we solve the problem using the first method, just the two equations and solve the two equations. Next, we can talk about how to use the formula. So let's talk about the method 2. So method 2, a formula for the variation of parameters. Formula for variation of parameters. Formula for the variation of parameters. So what we can do, there are a few steps. So the goal is to solve the non-homogeneous equation, but what we normally do is we can start with the homogeneous equation. So find linearly independent find two linearly independent solutions of the homogeneous equation. Homogeneous equation, which is y double prime plus pxy prime plus qx equals 0. So let them be y1 and y2, and then what we can do, we're going to find a particular solution. So the particular solution of the non-homogeneous equation y double prime pxy prime plus qxy if equal fx is given by is simply yp equal what we normally do is we write y2 first. So y2, y1 fx over the Wronskian of y1 first and then y2 dx minus y1 y2 fx over the same Wronskian y1 y2 dx. So that is the formula for the variation of parameters, and you can use this directly. Okay, so let's do a problem to see how it works. So let's do this one. So the example, find the general solution of x to the 4th power y double prime minus 2 x to the 4th power y prime plus x to the 4th power y equal ex. So we have that. So the answer, what we can do, we can look at the homogeneous. We can actually first divide by x to the 4th. So dividing by x to the 4th, the whole equation, then you're going to get y double prime minus 2 y prime plus y equal ex divided by x to the 4th power. And you can see, if you look at the non-homogeneous part, that is a constant coefficient equation. So the characteristic equation of the homogeneous equation is lambda squared minus 2 lambda squared minus 2 lambda plus lambda equals 0. That's what you get for the homogeneous equation. So we only look at the homogeneous equation. And what are the roots? You can see the roots are 1, 1. So the zeros are lambda equal 1, 1. Those are so thus we can write the solution yc. So yc is a repeated solution situation. So we know that it is c1 plus c2x e to the lambda equal 1, so it's x. So what we normally do is we can split this. Once you split, you're going to get c1 ex plus c2 x ex. And then you can see we're going to pick this one as one solution, this one as the other solution, y1 and y2. So let y1 equal e to the x and y2 equal x e to the x. Those are y1 and y2. Are two linearly independent solutions. And we proved that this is linearly independent earlier. So now what we're going to do, we're going to find the Wronskian. So it's w y1 y2. So the Wronskian of 2 is y1 prime y2 prime. That's the Wronskian. So let's plug in there. So if you plug in there, you're going to get ex. The derivative of ex is ex again. This is x ex. So derivative, you have to use the product rule. So if you use the product rule, you're going to get ex plus x ex. And now you're going to multiply. So you're going to multiply this first and then subtract that product. So if you do that, what do you get? You're going to get ex times ex plus x ex minus ex times x ex. So you can see this simplifies very well. That and that get cancelled. So you simply get e to the x times e to the x, which is e to the 2x, and you know that this never equal to 0. So that's good. Now what we're going to do, we're going to plug into the formula. So if you plug into the formula, So then you can see from the formula, so the particular solution is the particular solution yp is we can just write the formula once. So y2, which is y1 fx over w y1 y2 dx minus y1 see u2 fx y2 fx w y1 y2 dx. So let's plug in here. So if you plug in, you're going to get ex integral of ex, and then this is ex over x to the 4th power. The Wronskian is e to the 2x dx minus ex. This is x ex. Fx is still the same, so fx over x to the 4th power divided by e to the 2x dx. And you can see a lot of terms get cancelled. For example, e to the 2x and those two get cancelled, e to the 2x, those two get cancelled. So then you have, and remember please, you cannot bring anything inside or outside because those are functions, and it's going to integrate with respect to the same variable, so you cannot take anything outside. So x ex, this simply becomes 1 over x to the 4th power dx minus ex. This simply becomes 1 over x to the 3rd power dx. So these are very easy to integrate. You can bring it to the top and then integrate. So that means your answer is going to be, if you bring it to the top, is x to the 4th power. So it is x to the negative 3 divided by negative 3 negative e to the x. And this is going to be e to the, not ex. So you see that x to the negative 2 divided by negative 2. So if you simplify, you're going to get, so you're going to get negative 1/3 ex over x squared, and this can be 1/2 ex over x squared. So this you can simplify very easily. So you're going to get 1 over 6 ex over x squared. So then we can, so that's the yp, then we can write the general solution. So therefore the general solution is y equal yc plus yp, which is equals to c1 ex plus c2 not ex, yeah, c2 x ex plus e to the x 6 x squared. So that is the solution of the non-homogeneous equation. So that's the end of variation of parameters method.